Well, it's very nice to talk. Of course, I wish I was in person, especially because I think you probably have a much better weather than I do. But all right. So I want to present today a very recent paper that we finished just a month ago with Didier Brèche and Ron Soler, and which does two things. It solves for the first time the full mean field limit of the Vlasov-Poisson-Fokker-Planck equation. And the second point is it does that in a very simple manner. So I'll try to explain all of this today. All right. So to start with a relatively quick introduction, because I'm assuming that many of you are actually very familiar with the system and the questions behind that. So what are we trying to do? We are considering the dynamics of point charges. Right? With Coulomb interaction. And so typically, if we follow Newton's law and just use Coulomb force, this leads to the following very well-known many particle system. Right? So the particles are described by their positions and velocity. Xi is the position, Vi is the velocity. I'm going to use the mean field scaling. I'll say one quick word about that in a minute. And then we have pairwise interaction. And here I'm also going to add some diffusion. So in here, Xi is the position of particle I. It depends on time, of course. Vi is the velocity of particle I. All particles are identical, so they have the same charges, they have the same masses. Right? And K is the interaction kernel. I'm going to leave it as K for most of the talk, so that the assumptions that I need to make on the kernel to get the mean field limit are a little bit more transparent. But here, of course, right, K is going to be minus gradient of the potential, and the potential phi is going to be the electrostatic potential. So generally speaking, something like this, minus 2 if E is larger or equal than 3. Or okay, dimension. So this is in itself a very well-known system. Again, this is something that people have been aware of since the work by Coulomb at the end of the 18th century. The only slightly more recent contribution is are twofolds, right? First of all, there's this 1/n in front of everything, which is what is called as the mean field scaling. And as you are probably aware of, this is not the only scaling that one can put in front of the system. I usually like to say that it's the easiest, interesting scaling that one can put there. Easiest interesting in the sense that it makes the sum of interactions formally of order 1. So it sort of guarantees that the interaction will have the same scale, the same time scale in particular as the free transform. And the other term that I added here is this diffusion term, where all Wi's are n independent Brownian motions. And in the case of particles in electrostatic interactions like this, right, the canonical application is plasma, of course. And for plasmas, you very often have this kind of diffusive term because they represent some sort of random collision against the background. For example, you consider the electrons in the plasmas, they are much faster than the ions, so you freeze the ions, it's a sort of random background, and then you have those random collisions that you model as a Brownian motion. So this is a very well-known, very, well, basic, I would say, system in mathematical physics that have been studied extensively for a long time. And of course, the big question is that n is very, very large in for most applications, right? Plasmas, you think Avogadro number, so 10 to the 20, 10 to the 25 particles. And for this reason, of course, you would be very interested in deriving instead a continuum limit for that. And the notion of continuum limit that we know here has been introduced by Vlasov in the 1930s. And it's the mean field, what we call now the mean field limit, and it gives the famous Vlasov-Poisson-Fokker-Planck because of diffusion. And the mean field limit now consists in writing a statistical formulation of the distribution of particles. And because you need their position and their velocity, the minimum statistical information that you're going to require is the one particle distribution, which I'm going to denote F, right? So it's an F of Txv, which is the one particle distribution at time t. And what Vlasov showed using concepts of mean field is that this one particle distribution solves a nonlinear PD, which is the Vlasov-Poisson-Fokker-Planck equation. And where rho of Tx is just the one particle distribution, but only in position. All right, so so if I'm calling this Vlasov-Poisson-Fokker-Planck, right? Then ever since the this is the Coulomb system, ever since this has been introduced, right? A very big question, both in math and mathematical physics, has been to try to understand whether it's possible to rigorously justify the derivation of the continuum limit from the discrete system. Now, there's two small things that I want to emphasize before I give a tiny bit of literature. The first one is, of course, here, the diffusion is degenerate. Right? And you can see that because the Laplacian that shows up in the system is only in the velocity variable. By the way, I didn't put any friction in velocity here. Sometimes people prefer to write Fokker-Planck systems with friction in velocity. If you want to add that, that doesn't make any difference for what I'm going to say. Right. And the second thing that will play actually a very significant role in our proof is the fact that the convolution here with the interaction kernel involves not the full one-particle distribution, but again, only the projection of a one-particle distribution, so in space. And the fact that we integrate and that we have to integrate in the velocity variable, this is going to play a very big role. All right, so question of the mean field limit, whether at the deterministic level or at the stochastic level, they have been extensively studied ever since Vlasov. And so what do we know how to do? So some literature, I'm not going to cite everyone here. This would take a very long time. There's been a lot of great contributions. So I'm just going to highlight a few of them, the ones that are, I think, are the most relevant for what I'm going to present later. Now, the first works are actually done in the case where K is Lipschitz, right? So W1 infinity. And in the stochastic case, you have the very famous work by Maxine. So much so that in general, as you know, right, this class of equation is now usually called the Maxine-Vlasov equation. And in the deterministic case, if your sigma is equal to 0, you have a very famous work as well by Brown and Hepp and Dobrushin at the end of the 70s. Mackin was 60s. All right. Now, for first order system, so no velocity, right? Just xi, no vi. We actually know a lot more, and we know a lot more in for singular cases, so for cases that are not Lipschitz. And I'm not going to describe this. Again, there's a whole lot of results. Including some very recent work. But for second order system, the list is unfortunately much shorter. And so we had a couple of papers with Maxime Oret. Last one was about well, almost 10 years ago now. But those require that the singularity should only be mild, and so it has to be less than 1 over x asymptotically. So in particular, it cannot even cover it cannot even cover Vlasov-Poisson in dimension 2, and this is not compatible with any noise. And then you have a lot of results with truncated kernels. Right, so the idea of truncating the kernel is simply to regularize, so at some scale. So for example, you can look at the kernel K epsilon, which is still a potential, right? It derives from a potential, but now you could take the potential like this. Right? So you kill the singularity, but you kill it at some small scale. And then everything boils down to how small can you take that epsilon. And so there's a lot of results there. The best and most recent ones are around Peter Pickle. So yeah, where's Lazarovici? Pickle, that's for sigma is equal to sigma is equal to 0, and then this actually can this can be extended to the case of the stochastic question, and that was done by Liu and Pickle. But in terms of second order system with a singularity, that is pretty much it. And so, as you can see, we were very, very far from the Colombian type of interaction here. And this had remained quite a big open question and a very frustrating one for me because I've worked on that for a long time. And right, sometimes in cases like that, it turns out that when you finally find the solution, it's extremely technical and you understand why it took you a long time. And at other times, the solution is actually exceedingly simple, and then you don't understand why it took you so long. And luckily for you, because I'm going to present it, we are in the second case. Now, I should say that what I'm about to say, however, requires diffusion. And I'm going to take the positions on the torus. The velocity will be in the free space. And before going to the second order system, I will illustrate the basic idea of the method on a first order system on the torus. So the confined case. Now, it will turn out that second order or first order does not really matter that much for the method. The big question is whether you know a priori that all your trajectories are bounded or you don't. And so the fact that it's first order here is not very relevant because the fact that I'm going to take this on the torus and they are not unbounded velocity, this is what simplifies. So I'm going to consider the similar dynamics. And the limit now is written on the one particle distribution again, but since there's no velocity, I'm going to denote this one particle distribution by rho to remain consistent with the second order case. And I'm going to jump right in, and I'm going to write a theorem here. And so here, the xi are, for simplicity, going to be on the torus. You can take a bounded domain with the right boundary condition. So as usual, if you take a bounded domain, right, some boundary condition will work exactly the same, and then you're good. and others will not, and then too bad. And the theorem here will be very simple. And what I'm going to claim is that in a case like that, you always have the mean field limit, except for attractive singular gradient flow. Any other case, any model basically that you can give me, I can show the mean field limit. So let's call this M for macroscopic. So I'm going to assume that rho is a smooth solution to M. And I'm going to assume that K is in LP for some P strictly larger than 1. And I need an assumption on the divergence of K and only on the negative part of the divergence of K. The positive part can do whatever it wants. The negative part of the divergence of K, I'm going to assume that it's bound. Now, I'm going to assume that the initial position are IID to make my life simpler. And IID, according to the same distribution as rho. Okay, let's keep things as simple as we can. Right, and again, rho 0 is something that is bounded. Then you have a mean field limit. And you have a mean field limit in the sense that any marginal of a system is going to converge at least weak star to the corresponding tensorized version. So I'm going to denote by rho and k the k marginal, right? Which is just the partial law. It's the law. Since the particles are indistinguishable, I can pick any k of them. So it's the law of x1, xk at p. Then rho and k converges weak star to rho tensorized k. Right? So you have propagation of chaos and you have the mean field limit. So you see why I'm saying that in that case, it essentially always works. And you're going to have problems finding an interaction kernel that is not in LP. And so the only big requirement here on the interaction kernel is this bound on the negative part of the divergence. And again, if you look at what kind of models would actually violate that, well, if K is a gradient flow, right? So K is gradient of something, and it's attractive, then that's exactly when divergence K minus could be unbounded. So that's the one example I have of things where the assumptions here are violated. So this looks like a very an almost universal result. And as I claimed, the proof of this result is almost elementary. And we are going to start with the BBGKY hierarchy. Right? If we are going to say something on the marginals, then well, the BBGKY hierarchy is a relatively natural candidate. And this is normally something that is very, very hard to handle, but not here. So what does it look like? It is the following system of equation, right, on the rho n k. And you have two interaction terms, right? Because now you're considering a particle I from the x1, xk in rho k, right? And then everything depends whether this particle I will interact with a particle j, which is also in the x1 and xk, sorry, or with xj for j, which is strictly larger than k. So the first part, you have a self-contained equation, but in the second part, right, you would need the joint law of x1, xk plus xj. And so this involves the next order marginal, right, the rho k plus 1. Again, since everyone is, all particles are identical, right, whether j now is k plus 1 or it's n doesn't make any difference. So it gives you the additional term that you can write like this. To forget the n. And of course, you have the diffusion. Okay. Now, in general, this is a very painful system to try to work with because whatever you're trying to do on rho n k involves rho n k plus 1. But here there is a very simple trick. And that was actually noticed not that long ago in two separate papers. One paper by Lacker, where it was using the Gibbs entropy, so based on L log L, and then a paper that we wrote with Poyato and Soler about the case of a very different setting. And what happens there is that we said we can actually propagate LP bounds on rho nk. And everything works well because we have a non-vanishing diffusion. And so normally we would lose a derivative every time we're trying to do this, and we would end up in some crazy analytical space. But here there's no need to, just by doing a few quick folders. And so I am going to do this. I am going to try to propagate an LP bound. And so you multiply this equation by rho nk to the power p minus 1, and you do everything. Okay. And the first term here, well, will lead to terms with a divergence of k. And so let me make my life simple during this proof, just to avoid having a few extra terms, right? Let me assume that the divergence of k has a sign, which I know is not really possible on the torus, but okay. Otherwise, just put back the right term. So then with this, I have actually zero contribution from this first term, from the sum of I less than k and the sum of j less. And otherwise, you would have an extra Granville type of term. So we only have to look at those two, right? This term involving the next order marginal and the term with diffusion. And so if I'm integrating directly everything by parts, what I have for the first term is something like p minus 1 n minus k over n, the sum of I less k, and then I have the integral of gradient xi, okay, and the integral of k I minus x1. Oh. Okay. And k plus 1, dx k plus 1, dx1, dxk. And this is minus p minus 1, sigma square over 2, the sum over I of the integral of rho n k, p minus 2, gradient xi of rho n k squared. Very, very trivial. And now what I'm going to do here is I'm going to say, well, this bad term, right? This bad term that involves an extra derivative, I'm just going to absorb it by using the dissipation due to the diffusion. And if I'm doing this with just a couple of Holder inequalities, so something that you could give to a master's student, you end up with the following type of estimate. Constant that depends on p that I don't want to track. An additional k, because here I have a sum of k terms, and they are all going to be the same in the end, but I have them. And then p, the LP norm of this average interaction using the next order marginal. Okay. And while that still doesn't look very, very good, now here you have a very simple regularizing effect that happens naturally if you're working on a confined domain, so the domain needs to be bounded. And that actually mimics very closely the kind of regularizing that you would get if you had a real convolution with a tensorized. And this you can do again with just one extra Holder estimate. Right, so let's take this integral. Okay. And let's do a Holder estimate inside. Then I have k xi minus x k plus 1, right, in the dual, so p star, pxk plus 1, p over p star, times rho n k plus 1, p, and now px1, pxk plus 1, and let's put tilde here so that there is no. And you see that because k depends on the difference, right, this integral right here in the middle is just the LP star norm of k. Depends on sigma here as well, and then I have k, and then I have the integral of rho n k plus 1. And this, it turns out, is nice. This is a system of coupled ODE. I still have a hierarchy of ODEs here because to bound the LP norm of rho n k, I need to bound the LP norm of rho n k plus 1. So I'm going to push that further and further and further, right, till I've reached the last one, so rho n, which is the full joint law, and its LP norm, I know what it is because it's propagated. And so here, if initially this behaves like, you know, some power, right, which is what you would expect, because again, initially this is tensorized, right? So this is the integral of rho 0 to the power p 8 times. So this is something we have, provided that rho 0 is nice, and I've assumed that it's nice. P is large enough, right, so that k LP star is finite, which I can always do if k is in one LP with p strictly larger than 1. Then actually I know how to solve this, and I can show that this remains bounded on a finite term interval. And there exists a T star, which is actually a T star of a dimension of P, of sigma, and all the constants showing up here, so R, but not N, such that this remains true. And you probably use the factor. And once you've propagated this kind of LP bound with this scaling, then it's very easy to pass to the mean field limit. I can actually do the same analysis on the limiting hierarchy. And I can show that I have a unique solution to the limiting hierarchy within this kind of bounds. And then, because every rho n k is bounded in LP and p is large, it's not a big deal to pass to the weak limit in each term here. It works. I'm confined, right? So weak star is absolutely zero issue. We have all the tightness in the world. we get a solution to the limiting Vlasov hierarchy. We can show uniqueness to the limiting Vlasov hierarchy for solutions that has satisfied the corresponding LP bounds, and everything is really very easy. Now, there's one thing here that I'm going to discuss a lot more when now I'm going to try to write a theorem for the actual Vlasov-Poisson-Fokker-Planck. And it's that this analysis, as it stands, right, naturally only works for short time. So I should be careful here. Add that. Now, in this confined case, it is very likely that we could improve this short time. So I don't think that's a very defining feature. And that's why, well, I'll discuss that once we have a result for the Vlasov-Poisson, where I think it's actually much more essential. Maybe I can stop half a minute here if there are any questions on this proof, since that was a little bit technical before I try to use that.
There's no question.
Okay. So now let's go to the actual Vlasov-Poisson-Fokker-Planck, right, which is the main thing here. All right. So first of all, what is the issue and why can't I just do the same proof? Well, with Vlasov-Poisson-Fokker-Planck, the issue is in appearance relatively simple. It's solving it that turns out to be complicated. And the issue is the following. Right, if you want to fit within the first order model, you should consider your k of x as a k of xv. Right? Because now I have this extra velocity variable. And if I consider the k of xv, and now I'm still going to take x on the torus, but I'm going to take v in the whole RD, because that wouldn't make any sense to force the velocities to be bounded. And if I am in a case like that, k of xv in LP star of pi d times RD, right, this is automatically, necessarily plus infinity. And so if I'm trying to just follow the previous proof, right, what I have is I have a plus infinity somewhere in an inequality and then everything. And that's not a complete surprise. It's not an actual surprise that, and it's not actually common to have this issue with mean field limits, but it's very common to have it when you're studying the limiting equation. And part of the problem with Vlasov type of equations, when you have velocities, is the velocities are unbounded. The equation, the force field in the equation is k convolved with rho. And if you have LP estimates on F, you cannot easily get LP estimates on rho because you need velocity decay as well. So that's altogether not an uncommon issue when you're studying the limiting equation. But here it's really vexing because it's not, well, it's not difficult to solve in the end, but I should say I know of no other way of solving it than what I'm going to show you here. Right. So the whole issue is having some sort of control on the velocity. And I need velocity decay, and I need a velocity decay that is going to be nice with respect to my tensorized object. And so what I would like to have is I would like to have Gaussian decay in velocity, which is compatible with the diffusion, so that's fine. But I don't know how to get this out of here. And so here things get a little bit more technical. I will use the actual energy of the system, but not the full energy because I need the decay on each marginal. So I will define a reduced energy, which is the energy of the system that is reduced to k particles. I'm going to have a little ek, right? And I'm going to put the kinetic energy. Now let me add a 1 as that makes for a slightly nicer estimate, right? And then here I would normally add the potential energy. But I'm only adding the piece of the potential energy that corresponds again to this system. And why am I doing all this? I am doing all this because my reduced, the dynamics on the reduced system, so the dynamics of the first part of the BBGKY hierarchy propagates this. So if I denote now LK, the corresponding operator, okay. Okay. And LK of EK is equal to 0. And so this reduced energy is propagated by the self-interaction part of the BBGKY hierarchy. And now I can have a corresponding theorem that is a lot more painful to write down than the previous one, unfortunately. So again, I'm going to assume that F is a nice solution to Vlasov-Poisson-Fokker-Planck. Right. I'm again going to assume that K is in LP. LP of a torus is strictly larger than 1. I'm going to assume that K derives from the potential. I didn't need that before. I need it now to define EK. And because I will want to use EK to control the Gaussian part, I need that what I'm adding, the potential energy, has a sign. And this is why, by the way, I'm limited to Coulombian interaction and I cannot do Newtonian interaction. So I can do Vlasov-Poisson-Fokker-Planck for repulsive for plasmas, but this method as it is does not apply, at least yet, to attractive interactions such as gravitational. even though it's the same singularity. And now I'm going to consider a solution, right? So some xi. And I'm going to need some extra assumptions also on their initial condition. And I'm going to write this in a slightly more general manner. Before, I had just assumed that they were IID. And here, what I need is that f and k 0, right? So the corresponding marginal at 0 in some LP times some exponential of some small parameter lambda ek. And I need that this is less or equal than some fixed given number to the power k for all k. And so, right here. Then everything works. And I have a weak star convergence. I actually have tightness. I'm not going to write it down. So it's also convergence in the tight topology of measure. Then this converges the right thing on some small fixed interval with T star independent. And this is the main result. Now, once you understand, I'm not going to show you the proof, I wouldn't have the time, but once you understand the previous one, doing the proof here is not very, very hard. And so I'm just going to finish here with 3 remarks. The proof consists in propagating, well, LP bounds, but weighted LP bounds so that they incorporate this decay in velocity that I need. And so it's something like that, fnk to the power p time exponential. And now here I need a lambda t, right? Vk. Why do I need a lambda t? Because diffusion is going to spread things, right? And I'm looking at Gaussian decay. So I need to spread also my weights in a corresponding manner. And you know that the heat kernel, right, is exponential x squared over t. That's the behavior. So lambda here needs to behave like 100. So you take something like that. Right? Otherwise, those kind of weights would be blown up simply by the diffusion in velocity. But that's the only place where this lambda t shows up. A second interesting remark is that this theorem, as it is, if you're in dimension 3 and more, it does not apply to IID initial distribution. And that's because if you take them IID, right, the problem is, again, in this exponential EK, right, I have an exponential of phi. And exponential phi is never finite in dimension 3 and more for Coulombian. So it's a small thing that I believe will be able to correct by splitting correctly the initial distribution, even though we have not done it. Essentially, what I am saying is that if you take the xi0 IID, there's a probability that you're going to start with a very, very large potential energy. Right? The probability is small, but it's non-zero. And if there's a probability that you're going to start with a very, very large initial energy, it turns out that this probability does not decay fast enough in terms of the singularity of the energy. So this is probably a matter of doing some technical iteration on the initial condition. As I mentioned, the result is 1 month old, so I don't have the solution out of my head right now, but I wouldn't be surprised if this is something that we can do for that. And the third remark is, in a case like that, and the way I've written the theorem and the way I have a proof, for sure I need a short time. And the reason I need a short time is that this approach implies propagation of exponential moment and velocity in any dimension. And if it applies to f and k, you pass to the limit, you'll get the same estimate on the limit. So this implies propagation of Gaussian velocity moment on Vlasov-Poisson-Fokker-Planck in any dimension. And this is not true beyond a fixed time interval if the dimension is larger or equal than 4. We have counterexample. So here you see there is a very good reason why this kind of approach is going to be limited to short time. Now, again, there might be technical solution down the line here by saying, well, if actually we have a nice, smooth, and with enough decay solution at the limit, then we might be able to extend this time either by bootstrapping or again doing a slightly more clever decomposition of the solution. This is mostly everything. So as you can see, it's really a fun result. In the sense that it solves a long-standing conjecture on an important model. And it solves it with a proof that is, well, could have easily been done 30, 40 years ago. It doesn't really use any sophisticated technique, right? The worst that shows up are Holder inequalities. But it does use in a clever manner the regularity provided by the diffusion. And in the second order case, again, you need to be clever enough to add the right exponential weights to obtain velocity decay. So, right, I think there's obviously more work needed there, but I would expect that we are going to be able to do a lot of Minkle limit for non-vanishing diffusion with this kind of very straightforward approach. Thank you very much.
So are there questions for Pierre-Emmanuel?
Hi. Yeah, I have a question. So you mentioned at some point Daniel Lacker's work on the log L estimates.
Yes.
So if I remember well, what he gets out of his method is a rate of convergence in 1 over n squared for propagation of chaos. Is there a similar quantitative estimate for LP?
Okay, so that's something I didn't want to talk about because I was afraid it would be too long, so thank you for asking the question.
Okay. Sorry.
All right. So this is connected, if you want, with remark number 4, which is that so far this is purely qualitative. And can we make a quantitative estimate out of that? If k is at least in L2, I know how to do it.
Okay.
And then yes, you find the same, improved rate of convergence that Lacker had, right? Which, well, essentially, if you normalize instead of 1 over square root of n, right, which is what you would expect from a low large number, you get 1 over.
Okay.
I think there should be a way of doing this if k is just in LP with p possibly less than 2. Again, this is for future work, right? We couldn't solve everything at once. But I think it should be doable. It's also connected to remark 2 and remark 3, as a matter of fact. Because if we had good quantitative estimates, so then now in the propagation of LP bounds, we would use the limit. And now we could assume that initially we had strong convergence, so initially things would be small, and that smallness would likely be able to solve the problem of finite time. So then you would get the mean field limit also for any arbitrary fixed interval, not only for a short time.
Okay, thanks.
No more question? Okay, so let's thank Pierre-Emmanuel again for the nice talk.